Welcome back. In today's lecture, we will discuss a development in dimensional analysis known as Hunter's extension, which is used to extend the dimensional group to reduce the number of non-dimensional pies. One of the many irritants with the dimensional analysis is that there are too many independent pi numbers. Ideally, there should be one pi number. That pi number should be invariant, and this would be the best result that is available. If there are two pi numbers, one dependent and one independent, then a dependent pi number can be written as a function of the independent pi number. But we do not know what the functional dependence is. So you need a lot of experiments to determine that functional dependence. We have seen that for free convection on a plate, the Nusselt's number, the non-dimensional dependent parameter Nusselt's number, is given as a function of Prandtl number and Grashof number. There are three pi numbers involved, one dependent and two independent. Because of this, we have no idea how the functional dependence on Prandtl number and Grashof number would be. Recall Buckingham pi theorem. The number of independent pi's in the problem is n minus k, where n is the number of independent quantities, while k is the number of quantities in the base set, the complete and independent. We had seen in the last lecture how the number n could be reduced by using physical information. In the case of problems in heat transfer, we said we could reduce the number of n by 1 by taking the temperature difference rather than the two individual temperatures as independent parameters. We also combined the density differences at G in one pi number in some problems. This can go only so far. Is there a way to increase the number k, that is, the number of quantities required in the base set? The number of quantities required in the base set is about the number of dimensions that are used. So can we increase the number of dimensions? So one way to reduce the number of independent pi's is to increase the number of dimensions required to express the independent parameters and variables. Huntley suggested that we could indeed do so. He pointed out that many quantities of dissimilar nature have same dimensional representation. Like the shear modulus and bulk modulus, both have the representation of F(L minus 2), force, and two dimensions of length in negative. Or in MLT system as L minus 1, M, T minus 2. The two quantities are of different nature altogether, but they have the same dimensions. Torque and moment of a force have the same dimensions, Fl. Thermal conductivity and viscosity have same dimensions too. Plane angles and solid angles also have the same dimensions. No dimensions at all. Each element of a pair has the same unit and dimensions, but they aren't the same type of quantities. And therefore, dimensions representing the two functions should not be cancelled one against the other, because they are of a different physical nature. Similarly, the energy storage function and the inertia function of mass are two different things altogether. Huntley argued that we could differentiate between these two functions and create two separate dimensions. In this lecture and the next, we will do examples where we use this Huntley's extension and increase the number of dimensions required to express the quantities. He showed that the dimensions representing the two functions may be treated as different and may not be cancelled one against the other. We can represent two dimensions, m sub m and m sub I, respectively, for mass. The first one represents the quantity of matter, and the second, the inertial property of that matter. Consider the flow of a fluid through a pipe, a steady, fully developed flow through a pipe. The mass flow rate m dot would be a function of P prime, that is the pressure gradient along the pipe, the radius of the pipe, the density of the pipe, and mu, the viscosity of the fluid. If we express the dimensions of these five quantities, 1 dependent and 4 independent, in the MLT system, this is the matrix that we get. We have used mass as the same both for the inertia and for the flow rate. The basic set is P prime, the pressure gradient, rho, the density of the fluid, and r, the radius of the pipe. The three we have shown with the yellow tint in the table. The remaining two parameters, m dot, the dependent parameter, and mu, the independent parameter, the dimensions of this are expressed in terms of P prime, rho, and r. And if we do the algebra that was outlined in the last two lectures, we would get m dot, the dimension of m dot, the same as 1/2 the dimensions of P prime, 1/2 the dimension of rho, and 5/2 the dimension of r. Similarly for mu, 1/2, 1/2, and 3/2. With this table, we can write the two non-dimensional groups of parameters as m dot divided by square root of P prime rho r5 and mu divided by under root P prime rho r cubed. Not a very useful result. We'll have to do a lot of experiments to establish this functional relationship. However, Huntley suggested we can improve this by differentiating between the dual roles of mass as quantity of matter and as inertia in this case. If we do this, we now have 4-dimensional set, mi representing mass as the inertia, mm mass as the quantity of matter, and L and T. Then the 5 parameters, m dot, P prime, r, rho, and mu. Of these, the dimension m dot, the mass flow rate is easily written as mm raised to power 1 divided by t raised to power 1. So the dimensions are mm 1 and t minus 1. Mass flow rate, the quantity of matter flowing. Rho is very clear. The role of the mass here is quantity of matter. So it is written as mm raised to power 1 and L raised to power minus 3. Similarly, the radius of pipe is easily written as 1. But what about mu and p prime? We recognize that the dimension of mu should be the dimension of stress divided by dimension of velocity gradient from Newton's law of viscosity. This stress would be force divided by area, and the force is mass times the acceleration. But here, the role of mass is inertia, because inertial mass time acceleration would give you the force. So the dimensions of stress are expressed as mi L t raised to minus 2 divided by the dimension of area. So this quantity represents the dimension of stress. Here the mass has the role of inertia. The velocity gradient is simply L t minus 1 divided by L, velocity divided by length. And so the dimension of mu would be mi L minus 1 t minus 1. And this we put in the table. Next we look at the dimension of pressure gradient. And this would be pressure divided by length. And the pressure is force divided by area. So the dimension of P prime would be dimension of force divided by L cubed. And then force again is with mass in the inertial role. So the dimensions of the pressure gradient are m I L raised to power minus 2 t raised to power minus 2. And that we write in this line as mi1 L minus 2 t minus 2. This completes the table of dimensions. Now there are 4 dimensions. So the basic set would consist of 4 parameters with a yellow tint. And so we are left with only one other parameter, the dependent parameter. And we can easily construct the non-dimensional parameter with m dot as m dot by mu divided by p prime rho r raised to power 4. And this should be invariant between the bits, and this should be invariant between the model and the prototype. So we can write m dot as c times p prime rho r cube r raised to power 4 divided by mu. A single experiment would be enough to establish the value of c. Since there is only one pi number involved in this formulation of the problem, this is a very powerful result. So it should be apparent now that by increasing the dimensional set required to have one more member, and that we did by splitting mass in its dual role as inertial and as quantity of matter. So the value of R increased to 4, N was 5, so there's only one non-dimensional group of parameter, 1 pi, that was needed. Another thing that Huntley introduced was to consider the role of vectors. Various quantities like vector, velocity, acceleration, torque, momentum are vector quantities. And so is the area. Consider this object. The areas in this object are of two kinds. The drag on this object when a fluid flows past this depends on the lateral surface area. The end areas, the area of these ends, contribute to mass. So these two areas are of different kinds altogether. Again, consider two quantities, torque and work. A force F at a distance r from a point. The dimension of torque are L, the dimension of r, and the ml t minus 2, the dimension of force, to give you ml2 t raised to power minus 2. And the dimension of work when object moves through a distance x is fx. And the dimensions are same, ml2 t minus 2. But the distances involved, in one case r and one case x, are in different directions altogether. Torque divided by work or work divided by torque should not be a dimensionless parameter. The dimensions play different roles in there. Huntley argued that the length dimension should be treated as vector dimensions with three independent components Lx, Ly, and Lz. In Huntley's view, the measurement of length in the x direction is by its specification a different operational procedure from measurement of the length in the y direction, because the operations are carried out in different planes. The mathematical counterpart of this physical explanation is simply that in a vector equation it is never permissible to cancel an x component against a y or a z component of any vector quantities. Thus, we supplement three dimensions m, l, and t, and instead of L, we use Lx, Ly, and Lz. Three separate dimensions instead of one single L. So, the dimensions of the lateral area may be Lx, Ly, or Lx, Lz, or Ly, Lz. The dimension of volume would then be Lx, Ly, and Lz, product of these three. Shear drag on the lateral surface marked A would be mu times the velocity gradient times the area. The velocity gradient, if the flow is in that direction, the velocity is Lz divided by t, and we are talking of the gradient normal to this velocity gradient. So, the velocity gradient is obtained by dividing the velocity by Ly. And the area is of this surface, which is Lx, Lz. So, the dimensions of this would be tau is the same as mu Lx, Ly raised to power minus 1, Lz raised to power 2t minus 1. On the other hand, the pressure on the end face here would be the force, which would now be mLz t minus 2, since you are talking of the z direction. And the area on which it acts has a dimension Lx, Ly. So, dimension of this pressure would be m Lx minus 1, Ly minus 1, Lz t minus 2. torque, which is Rf, would be function mLx Ly t minus 2, and work would be mLx square t minus 2. In the simple MLT system, both would have dimension of ml square t minus 2. But we realize that in torque, the two lengths are in different directions, Lx and Ly, while in the work, they are in the same direction, Lx squared. Using these directions and writing dimensions in terms of these directional dimensions is not easy. We'll do a few exercises to get some practice. We start with a very simple example. A projectile is projected horizontally with a velocity u from a point at distance h above the ground. We have to find the range. And the range clearly would be a function of the initial velocity u, the height h from which it is projected horizontally, and acceleration due to gravity. If we do a simple-minded dimensional analysis like we have done in the previous classes, this is the dimensional table. There are only two dimensions involved, L and T. R and H would have dimension of length only. Velocity would have dimension of length and t minus 1. And G, of course, has a dimension of L, t minus 2 meters per second square. We use the basic group U and H, so we get R and G as the other parameters, one dependent and the other independent. And using this, we get the dimension of R as, in terms of U and H, as H for R and U square divided by H for G. So that our functional relationship would have 2 pi's, R by H and U square by GH. So that RH, the dependent one, can be written as function of U square by GH. We really have no idea of how this functional relationship should pan out. But this is a prime case for using directional analysis, for using 2 different dimensions for 2 different directions. Here, we use X, Z and T system. X for Lx and Z for Lz. So now, instead of L and T, we use X, Z and T system. The range R would be in X direction. The velocity is in X direction. So it is X minus T, and H is in Z direction, 1, and G is in vertical direction. So it should have a dimension of Z divided by T square, or Z1 T raised to power minus 2. In this, we use the 3 quantities U, H and G as the basic set. And so there is only one parameter that is left, the dependent parameter R, and the dimension of dependent parameter in terms of U, H and G is obtained as U raised to power 1, H raised to power half, G raised to power minus half, so that there is only one parameter that is formed. And that parameter can be written as R divided by capital U multiplied by under root G by H. And this should be invariant. It should have the same value in every experiment, whatever be the value of capital U, H, and G. So one experiment would establish the value of C in the relation R is equal to C, a constant, times U under root H by G. So this clearly established that using the directions as dimensions could simplify this projectile problem. We do more of projectile problems. Let's get a little more complicated. Now we have a horizontal plane and we project a projectile with a velocity u at an angle alpha to the horizontal. And we want to determine the range. The range clearly would be a function of u, angle alpha, and g, the acceleration due to gravity. We proceed in a simple-minded manner of using only the two dimensions, length and time. The dimensions of r, u, and g are simple. Alpha is dimensionless, so alpha itself is a parameter. We can use u and g as the basic set. So there is only one other parameter left, r, and we form the dimension of r as u2 u square g raised to minus 1 in alpha, so that the 2 pi numbers that are formed are r g by u square and alpha. And we can write r is equal to u square by g f of alpha. We have no idea what would be this function of alpha. So we resort to directional analysis. And while we do the directional analysis, a simple trick of converting u and alpha into ux and uz, the velocity in the x direction and the initial velocity in the z direction, which would be u cosine alpha and u sine alpha respectively. And we use x and z this direction, and the relevant directions are these. The dimensions of ux are clearly x1 and t minus 1, direction x, and dimensions of uz are z1 and t raised to minus 1. Dimensions of g is in the vertical direction, so it is z raised to power 1, t raised to minus 2. We need 3 elements in the basic group. We use all ux, uz, and g. Only one pi number would be formed, and that pi number has a dimension ux into uz divided by g. Then that should be constant. So that r, the range, is c, a constant, times ux, uy divided by g. For ux, we write u cosine alpha, and for uy, we write u sine alpha, so that the range can be written as a constant times u square sine 2 alpha divided by g. Only one experiment would be required to establish the value of c. We can go a little fancier. Now the same projectile is projected with the velocity capital U at an angle alpha, but now it is not thrown on a horizontal plane, but an inclined plane at an angle beta. And this time, our problem is to find the time of flight, the time tau of flight. For this, we use two directions, S and N. S along the plane and N normal to the plane. G is resolved a component G cosine beta normal to the plane and G sine beta along the plane in the negative direction. The time of flight is a function of us, the initial velocity along the plane s, the initial velocity along the plane s, and initial velocity normal to the plane un. And it depends upon the acceleration due to gravity in the normal direction. We construct the table with dimension S, N, and T. US has a dimension S1 and T minus 1, UN has a dimension of N minus 1 and T minus 1, and GN has a dimension of N1 and T minus 2. We need 3 parameters in the basic group, and so we have only one left, and we can construct the dimensions of tau in terms of US, UN, and GN using the methods outlined in the last couple of lectures. US 0, UN 1, and GN minus 1. And from this, we get only 1 pi tau G by UN. The time of flight tau is now constant times UN by G. And UN is seen to be U times sine alpha minus beta. And GN is cosine beta. And GN is G cosine beta. So the time of flight is C times U sine of alpha minus beta divided by G cosine beta. Again, a very powerful result in the sense a single experiment would establish the complete functional relationship. Let's do one more example. Energy of a vibrating stretched wire. Stretched wires, like the strings of a guitar, vibrate when plugged. The energy of these vibrating wires will depend upon the frequency n at which they are vibrating, the length L of the string, the linear density rho prime, that is the mass per unit length, and the amplitude A of the transverse vibrations. We work in MXZT system. Instead of the length dimension L, we use 2 dimensions, one X along the string and the other Z perpendicular to the string. Then E would have dimension of mass times the velocity squared, the velocity in the vertical direction. So it would have a dimension of Z2 and T minus 2. So that the dimensions of E are M1, Z2, and T minus 2. Similarly, we can write the dimensions of the other quantities, N, the frequency, rho prime, mass, per unit length in the x direction, and amplitude is in the z direction. Length also is in the x direction. There are 4 dimensions, so there are 4 parameters in the basic set, we choose n rho prime, a and l. The only choice we could have made, because the dependent parameter e is never chosen in the basic set. With this, we can write the dimension of E in terms of n rho prime, a and l, and they turn out to be n2 rho prime 1, a2 and l1, so that there is only one pi that is formed, E divided by n square rho prime l a square. Or we can write that the energy of the wire E is like constant times n square rho prime l a square. There is only one constant C that needs to be determined, and one single experiment could do that. If we had not used the vector length, there would have been two pi numbers, one dependent and one independent. The dependent prime number would have been E divided by n square rho prime l cubed, and the independent prime number would be A divided by L. Because A by L is small, so function of A by L would be of the form A by L raised to power alpha, with alpha undetermined. Thank you.